Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. We are going to begin looking at systems of nonlinear equations in this video series. So we're going to set this up so that we will write our systems of nonlinear equations as a function of a variety of x's set equal to 0. And if I have n unknowns, then I need to have n of these equations. Now, any of them might be linear, but if even one is nonlinear, then the entire system is deemed to be a nonlinear system of equations. Let's look at the Newton-Raphson technique. Now, we've done this before for just a single equation, and it was based on the Taylor series expansion, just a first-order Taylor series expansion. Now, I can do this for a system of two or more equations by using the appropriate form of the Taylor series for multiple variables. Now, we've got it set up here for a system of two equations with two unknowns. That's something that's fairly reasonable. It gets just messier the more variables you have and the more equations, but the system does indeed expand for as many variables as you need. But a first-order Taylor series expansion for function of x and y is going to be based on a starting point of the function at x and y times a delta x times the first derivative of the function with respect to that x, and plus delta y, my other variable, times the change in f1 with respect to the y. I'll evaluate these at my starting points, and I can do this for the second function. So f of 2 at my new point is f of 2 at the old point, plus delta x times the derivative of f2 with respect to xi, plus delta y times the derivative of f2 with respect to yi. Since our goal here is to find where f1 and f2 are equal to 0, we'll just declare them to be 0 and use that so that we can rearrange our equations, and we end up with negative f1 at xi, yi, and there's a closing parenthesis that got chopped off in my cut and paste, is equal to the first derivative of f with respect to xi, so a partial derivative with respect to x, times delta x, plus the partial derivative with respect to y times delta y, and negative f2 of xi, yi is going to be the same thing for function f2. Now, this is a system of two linear equations. So I still have two equations that need to be solved simultaneously, but now it's linear, and I have a whole slew of solution techniques available for that. One of the easiest is to set it up in matrix form. And so in this case, my x's really are these delta x's, and the partial derivatives form my matrix of coefficients A. Now, A is also going to be called the Jacobian for this system. My B is going to be my starting values, negative f1 and negative f2, at my initial point. Now, these values here for A can be found analytically if you have a functional description, or if you have data, you can do this using finite differences. So the forward finite difference, or the backward, or the central, depending on what information you have and how precise you want your answer to be. So we can evaluate these in a variety of ways, and we can solve this system of equations in a variety of ways. An algorithm recommendation is that you're going to start by guessing the values of all of your x's for however many equations you have. In the form we've written down, 2, so it would be x1 and x2. And then start your iterative technique. So initiate to I = 1 and evaluate each of your n functions at the initial guess. Use that then to calculate the Jacobian. Now this method shown here is for doing this using the determinant method, okay, Cramer's rule. And you can do that, but you also can use matrix inverses or any other solution technique for linear equations that you like. This is the summary of the determinant method. These are your loops set up, so you're doing your replacements. Okay, you're checking to see whether or not you're within the tolerances that you've said you're willing to accept. If not, you'll add 1 to your I value and go through the loop again. In our next video, we're going to look at actually doing this, applying this technique to an example problem. Thank you very much for your time.